Hello everyone, I am Chen. Today I'm very glad to present our work, Communication Efficient Federated Learning with Adaptive Parameter Phrasing. In recent years, federated learning has become a very hot research topic for edge computing. It enables distributed edge clients to collaborate in model training without disclosing the local private data. However, due to the poor network connection between the central server and the edge clients, gradient communication has become a severe bottleneck for federated learning. Given a machine learning model, the objective of the federated learning process is to minimize the loss function over the whole training dataset. A common training algorithm for that is stochastic gradient descent, which iteratively refines the model parameters towards the optimum. Under the SGD algorithm, a model parameter usually goes through the two phases: a transient phase where the values change drastically, and a stationary phase where the values oscillate around the optimums. When a parameter stabilizes in the stationary phase, its gradients are many random noises, and this is actually a wastage of the network bandwidth. We have confirmed that both theoretically and experimentally. In the right figure, we randomly sampled two parameters when training the LONET5 model on Cepher-10 dataset, and the values gradually stabilize when the model approaches the best accuracy. Moreover, we also observed that parameters in different layers, or even in the same layer, may stabilize at different epochs. Naturally, we can reduce the communication amount by not synchronizing the stabilized parameters. However, there are two challenges for that. First, how to identify the stabilized parameters in an efficient manner. Second, how to ensure model convergence when no longer synchronizing the full model. Regarding the first challenge, we propose a metric called effective perturbation, which describes the oscillating extent of a parameter. We judge a parameter as being stable if its effective perturbation is very close to zero. Regarding the second challenge, we first explored two candidate solutions. The first solution we explore is naive partial synchronization, which means to update the stable parameters only locally, excluding them from global synchronization. However, as shown in the top right figure, when training the LONET5 with this method, there is a huge accuracy loss of over 20%. We find that it is because the edge clients in federated learning usually host long IID data, and the local optimums are non-identical. As shown in the two figures, if we update the stabilized parameters only locally, on different clients their values would diverge to different optimums. Therefore, the first lesson we learn is that stabilized parameters must be kept consistent across different clients if they are not synchronized. The second solution we try is the permanent phrasing. That is, once a parameter becomes stable, we would no longer update it anymore. However, as shown in the top right figure, this method does not work either. Regarding the reasons behind, we find that some parameters only stabilize temporarily because of the complex interactions between different parameters in the model. Consequently, if we fix the value of the similarly stabilized parameters, they will not be able to reach the true optimum later. Therefore, a second lesson we learn is that our solution must work well for parameters that stabilize only temporarily. To summarize, in previous explorations, we learned that non-synchronized parameters must be frozen, and those frozen parameters should be able to resume updating later. Therefore, we propose to tentatively freeze a stabilized parameter for a particular freezing period. That period is adaptively tuned based on whether that parameter is still stable after resuming regular updating. In particular, we should greatly increase the freezing length if the parameter keeps stable, and should meanwhile react timely if a stable parameter has a strong drifting tendency. To control the freezing period, we designed a mechanism similar to TCP AIMD algorithm. That is, we additively increase and multiplicatively decrease the freezing period based on whether a parameter is still stable after the freezing period. Our solution is called adaptive parameter freezing, or APF. We have implemented APF as a Python module called APF Manager in PyTorch. The APF Manager packages the long frozen parameters into a tensor for efficient transmission. And after synchronization, it will restore the tensor into a full model. We have evaluated our APF implementation in a 50-node EC2 cluster emulating real-world battery learning scenarios. The three figures shows the instantaneous accuracy and the percentage of frozen parameters when training the NAT5, ResNet, and LSTM. In each case, APF can remarkably reduce the communication amount while preserving the model convergence accuracy. We also draw some other conclusions in our evaluations. We confirm that the AIMD design in APF is better than purely additive or purely multiplicative mechanisms. Meanwhile, as a specification method, APF is better than other specification methods in the literature like Gaia and CMFL. APF is also robust to hyperparameters, and its computation and memory overhead is low for edge devices. Please refer to our paper if you're interested in these evaluation details. Thanks for attending this presentation. Welcome for any questions and comments.